Chapter 11, the t-test for two related samples. The learning outcomes or objectives for this chapter are as follows. First, understand structure of research study appropriate for repeated measures t-hypothesis test. Test mean difference between two treatment conditions using repeated measures t-statistic. Evaluate effect size using Cohen's d, r-squared, and or confidence interval. And finally, explain pros and cons of repeat measures and independent measures studies. Tools you'll need to be successful with understanding material presented in this chapter. The introduction to the t-test, chapter 9. In fact, the equations we mastered in chapter 9 are very similar in this chapter. So if by any chance you're still having difficulty with the single sample t-test, I highly recommend you go back and review that material because again, this chapter is almost identical with slight variations. So we'll need the understanding of the single sample t-test, again that's chapter 9, that includes the estimated standard error, which is, the equation is as follows. We either take our variance over n and take the square root, or if we have the standard deviation, we take that and divide by the square root of n. The degrees of freedom for a single sample t-test is n minus 1. And the t-distribution, we should have familiarity with how to find our critical t given the alpha level, whether we are testing a one or two-tailed test hypothesis, and also degrees of freedom. And again, understanding the hypothesis test using a t-statistic. We'll have to have that knowledge in order to understand the process of engaging in a t-test for two related samples. And then it would be helpful to have mastery of the independent measures design discussed in Chapter 10. Again, the similarities between Chapter 9 and 11 are much greater, but it's good to reflect on what we did in Chapter 10. Again, briefly, Chapter 10 was looking at two independent sample means that represented two independent populations. As I just mentioned, in Chapter 11, we introduced the independent measures research design, also known as between subject design. And in that design, we were able to compare two treatment conditions or two populations. The independent measures design is characterized by the fact that two separate samples are used to obtain two sets of scores that are compared and representative of two different populations. In this chapter, we will examine an alternative strategy known as the repeat measures design, or often referred to as the within subject design. With a repeated measures design, two separate scores are obtained for each individual in the sample. For example, a group of patients could be measured before therapy and then measured again after therapy. Or response time could be measured in a driving simulation task for a group of individuals who are first tested when they are sober and then tested again after 2 alcoholic drinks. In each case, the same variable is being measured twice for the same set of individuals. That is, we are literally repeating measurements on the same sample. So again, the way that this type of test differs from what we did in Chapter 11 is that we are using the same subjects and exposing them to all levels of the independent variable. So again, as I just mentioned, we can use a sample of 10 individuals. Let's measure them before they receive treatment and then after. Again, it would have to be the same individuals for before and after scenario to work. Again, in the second example where we're measuring response time when driving for those who have not consumed any alcohol, and then we administer alcohol, we give these participants 2 drinks, 2 alcoholic drinks, and then see if their reaction time while driving has been affected. So again, we're using the same subjects. We're repeating the use of those individuals and exposing them to all levels of the independent variable or conditions of the independent variable. One of the main advantages of the repeated measure study is that it uses exactly the same individuals in all treatment conditions, which does a couple things. It minimizes the differences that we may anticipate in groups. So there's no risk of the participants in each group differing significantly from each other. One example that's cited in the text is that one group, if we're looking at GPA scores, initially one group may be faster, smarter, more extroverted, and other characteristics can be more positively demonstrated in one group versus the other, which is the disadvantage of the independent measures t-test. For repeated measures, this is an advantage of using the same individuals because in a sense we are holding all of those variables constant. Those individuals are bringing the same characteristics to the table in one condition, and we measure them. And then when they're exposed to the next condition, it's the same individuals with all the same characteristics. So we don't have that, the potential of having differences, significant difference in the characteristics that these participants bring to the table. Again, if we're looking at GPAs and by chance, one group tends to have higher GPAs to begin with, and then we use a treatment of exposing them to intense tutoring programs. The fact that we started off with differences in the different categories sets us up for essentially invalid results in the end. So again, this is an advantage. It's holding also the variability that we see. In the previous chapter, we had to pool the variability of the two groups. In this case, we're again holding that variability constant. We're holding it constant and the same across all conditions because we're working with the same individuals. A hybrid design that incorporates some of the elements of the independent measures t-test and the repeated measures t-test is referred to as the match subject design. The match subject design approximates the advantages of the repeated measures design. Again, the advantage is that we're working with the same individuals, and it approximates that design by, again, having two separate samples. But what's different is that each individual in a sample is matched one-to-one with an individual in the other sample and matched on relevant variables. So you can think of it as their twin. So it's not the same person, but it's a person that looks very similar to them based on certain variables that are important to that particular study. So again, this is a bit of a hybrid between the independent measures t-test and the repeated measures design. It is used because it takes advantage of the fact that repeated measures design holds variability constant across the conditions, and but it is taking elements from the independent measures t-test by having separate individuals in each condition. So participants are not identical to their match, but nonetheless it ensures that the samples are equivalent with respect to some specific variables. So they're not going to be exactly the same, but we're going to focus on certain variables that are important. An example from the text says that a researcher could match pairs of subjects on age, gender, race, and IQ. So those, for a particular reason, are important variables. And so we would, in this case, a 22-year-old white female with an IQ of 115 would be placed in one sample, and then matched with another 22-year-old white female with an IQ of 115 in the second sample. So again, using two independent individuals allocated to the two different conditions, but they're matched based on these specific variables that have been identified as important to hold constant in this particular research. So under the category of related samples design, we recognize that it encompasses both of these processes. One is the repeated measures, where we're working with the same individuals and exposing them to all conditions of the independent variable, or we recognize that it also includes the match subject design, where we're taking individuals and matching them one for one based on specific variables. Both of these designs are statistically equivalent, meaning that even though we are using two different groups, as in the case of matched subject design, they're two different individuals, we would still use the calculations specific to the repeated measures design that will be presented in this chapter. So again, don't get confused that if you are conducting a matched subject design, first, again, you recognize they're two different groups of individuals, but they have been matched. So the tendency may be that because they're two different groups of individuals, you want to use the independent measures t-test process. But if it's been specified that they have been matched one for one in these different conditions, then you would use the calculations for the repeated measures design. So I will present those calculations in just a moment. So we should recognize that we'll talk more about this later, but one of the disadvantages of the matched subject design and the independent measures t-test is that it requires more subjects. So again, in the independent measures t-test, chapter 10, if we have two different conditions and we want a minimum of 10 individuals per condition, we need a total of 20 individuals to participate in our study. One of the advantages here is that we're recycling these individuals using the repeated measures design. So if I want 10 individuals per condition, I only need a total of 10 individuals because they will be exposed to all levels of the independent variable. So we'll talk more at the conclusion of this chapter about the advantages and disadvantages. But at this point, we recognize that the matched subject design is disadvantaged in the sense that we do need more participants because each condition is made up of different individuals. The t-statistic for repeated measures research design is very similar to the other t-statistic. So here on the right, I've indicated what the basic structure is for t-statistic. The numerator is always the mean difference, and the denominator represents the standard error. So this t-equation for chapter 11 is essentially the same as a single sample t-test. So let's review what the t-equation looked like for chapter 9. And again, chapter 9 was a single sample t-test. And our t was equal to our sample mean minus the population mean, which was a known value, over the estimated standard error of the mean. For chapter 11, this chapter, the repeated measures t-test, our t-equation is as follows. T is equal to m sub d, which is the mean of the difference scores, minus mu d, which is coming from the null. The null would indicate that there is a zero difference between condition 1 and condition 2, over the estimated standard error of the mean difference. So notice how they are alike, but also how they are different. So again, it's still the basic structure of the mean difference denoted in the numerator and the standard error in the denominator. But again, this new character, the sub D label, comes from this concept of difference. So it's based on difference scores rather than raw scores. So our new variable of D is calculated by x sub 2 minus x sub 1. X sub 2, for the example of before and after treatment, x sub 2 would represent the participant's score after treatment, and x sub 1 would be their score before treatment. So we take how they performed in both of these conditions and compute the difference between the two conditions. And then what we can also do once we've calculated all the D scores for all of our participants, so again, every participant is going to have 2 scores. In this example, their before therapy score and their after therapy score. And then we can produce this new column that we would refer to as the difference that expresses how different these two conditions were. And then given those values, then we can compute the sum of all D scores, the sum of the different scores, and divide by how many pairs of scores we have to compute this new statistic referred to as the mean difference. And that's what we see here, the mean difference. So instead of just working with the actual mean of our X values, again, the M statistic is calculated by taking the sum of X dividing by N. So again, notice instead of working with an X distribution, as we indicated up here, we're now working with our D scores, which is simply the difference between condition 1 and condition 2. So let's use table 11.1 to better understand this new character that we refer to as D or difference scores. So this represents participant or matched pairs. So we have this many matched pairs or before and after scores. So we have 5. N is equal to 5. And then first score is denoted by X sub 1. Second score is X sub 2. So this is the second treatment, right? But again, it's the same person. So in number 1, these two scores relate to one individual. So their second score and their first score. So to compute the difference score, again, difference score is equal to X sub 2 minus X sub 1. So we'll create a new column that we refer to as D. So 15 minus 12 gives us 3. 14 minus 10, 4. 17 minus 15, 2. 17 minus 17, 0. And 18 minus 12 is equal to 6. And then now that we have our difference scores, we can take the summation and also compute the average score of the differences. So we begin with the sum of D is equal to, so we have 6, 4, 10 is equal to 15. And then we can compute the average of the difference scores. So we take the sum of D over N. We have a sum of D equal to 15. We have 5 scores, and that produces an average difference score equal to 3. So again, this is the process that we would follow to then use our t-statistic equation, which is the mean difference minus the population mean difference over the estimated standard error of the mean difference. And again, this is coming from the null that says there is no difference, so it equals 0. And again, we just computed what our average difference is. So now we'll need to talk about what this represents and how to calculate the standard error for a t-test of repeated measures. So again, we have here the equation for our repeated measures t-statistic. And let me just provide what the t-statistic look like, or the equation for Chapter 9, a single sample t-test, just so that we can use what we've already learned and add to it by recognizing the similarities. So the t equation, again, as I stated previously, is the sample mean minus the known population mean over the estimated standard error of the mean. And the estimated standard error of the mean, one equation, was equal to taking our variance over n and then taking the square root. So now we're going to talk about what this is equal to in the repeated measures t-test. So our equation is illustrated here. The estimated standard error of the mean difference is equal to the variance over n, and we take the square root. So the equations are identical. But what's different is that this variance is the variance of our D scores. So again, we just showed how to produce our D values. D is equal to X sub 2 minus X sub 1. So we created a whole distribution of D scores. And now, given our equation of how to calculate variance, we can now produce the sum of squared deviations for our d-scores, and I'll show you how to do that. But again, what differs from what we did in Chapter 9 is that this variance, this score here, relates to the variance of the d values, the difference scores that were calculated using this equation. So let's go back to our table to see how this would look with some real numbers. So again, these are the data points that we had for our repeated measures. So the same individuals, their second score minus their first score produce our different scores. And now we need to calculate our variance. So variance is equal to SS over degrees of freedom. So we need to calculate SS, and we can use the computational formula. In the previous chapter, in chapter 4, we learned that SS was equal to the sum of x squared minus the sum of x squared over n. But again, we're not working with x values now. We have this new distribution of d values. So we're just going to change all of the x values to represent d scores. So now instead, our equation would read the sum of d values that have been squared, and in here we're going to take the sum of our d scores, which we have already calculated, right? That this was the sum of d here. So we know that that's going to go right into the parentheses there. And well, why don't we go ahead and replace the variables that we already know. So again, we know that in the parentheses, that's representative of the sum of difference scores. That's equal to 15. We're going to square that. We know that the sample size is equal to 5, and what we don't know yet is this variable here, the sum of all d values that have been squared. So all we need to do is square all of our d scores and then take the summation. So 3 squared, 9, 16, 4, 0, and 36. And now that we've computed all the individual d values and squared them, we take the summation. And the sum of all d values that have been squared, sum of d squared is equal to 65, so we can put that into our equation. So now to solve for the sum of squared deviations, we take 15 squared divided by 5 in our calculators. That should give us 45. So 65 minus 45 gives us 20. And now we've produced the sum of squared deviations for our d distribution, and that value would then be used to compute our variance. So here's our equation for our variance. So it's SS, which we just calculated, is equal to 20. Degrees of freedom, again, it's similar to Chapter 9. We're just working with one group of individuals, so degrees of freedom is equal to n minus 1, which is equal to 5 minus 1, and we get 4. So 20 divided by 4 gives us 5. And thus we have now computed the variance of our d distribution, of our d scores, and we could use that to then calculate our estimated standard error of the mean difference. So we can then compute, given what we just calculated for variance, we would take variance was equal to 5, our sample size was equal to 5, and that would equal the square root of 1. And given the data presented in table 11.1, we've come up with the estimated standard error of the mean difference equal to 1. And we would use that in our t equation to compute our t statistic for repeated measures design. So now that I've presented the variables that pertain to calculating a t-statistic for repeated measures design, it's a good idea to present what the notation would look like for the research and null hypothesis. So the first represents the null. The null says that the mean difference will equal 0. In other words, if, again, we're taking one individual and recording their scores in these two different conditions, so the null is going to say that their scores are not going to differ, that once they're exposed to the next condition, their different scores would equal 0. And again, this is the average, and this would pertain to every participant, that every time that they're measured with the two different conditions, the null is saying that we will expect 0 difference between the two conditions. And when we represent that in the distribution, again in the center, we would say that mu d is equal to 0. Again, that's representative of the null hypothesis. The alternative research hypothesis would say that the average difference would not equal 0, that we would see some difference between the conditions. So again, this is both of these, the way that they're stated in the notation that goes along with it, is applicable to two-tailed test, hypothesis test, or non-directional, because again, we're not specifying that the direction is going to be greater or less. We just expect there to be no difference given the null. We don't expect that condition 2 will produce anything different than condition 1. And again, it's two-tailed because we just see the equal and not equal sign. So I'd like to also illustrate what it would look like if we are working with a directional hypothesis. So one-tailed test. So we would say the research hypothesis is one option. We may say that the mean difference is greater than 0, and the null says that the mean difference is less than or equal to 0. So let's just talk about this for a second. If I anticipate that the mean difference will be greater than 0, then what I'm saying is that condition 2 will produce higher scores, because again, D is equal to condition 2 score minus condition 1 score. So if I'm producing a value that's greater than 0, that's a positive number. Therefore, this number, I'm assuming that the second condition will produce higher scores than the first condition. And of course, as always, the null is going to state the opposite and always include the 0. So the null is saying that the conditions will produce equal scores, or the null is saying that condition 2 is less than condition 1. Because again, if we're taking a score that's the first score here, if that number, excuse me, is equal to, let's say, 9, and the second score is equal to 10, notice the second one, which represents actually the first condition, is higher, then we would have a negative value. So again, keep in mind what exactly the hypothesis is indicating in terms of direction. So if we go back to this one, again, what I didn't show you, so D is equal to x sub 2 minus x sub 1. If we expect that the mean difference to be greater than 0, that means we'll have an average that's a positive number. So let's say it looked like for the first set of scores, then that would be a positive 1 D value, and that overall we would expect a positive average of those different scores. Versus in this example, we would expect that the average of the different scores is less than 0, so that we would be stating that the second condition produced lesser scores. Let's say, for example, you're testing a new blood pressure medicine, and you would expect that the blood pressure medicine is going to reduce blood pressure. So again, the average difference anticipated would be something less than 0, because we expect it to be effective and decrease the scores. So before we move on to something else, I just want to compare what the chapter 9, the single sample t-test, look like in terms of the notation for the research and the null hypothesis. So for a single sample t-test, we would have a known mu. Let's say we're comparing the IQ of engineering majors to the IQ of psychology majors. And we say that the average IQ of engineering majors is 120. And then we would sample psychology majors and then determine if there's a difference. So the null would state that the mu of the psychology majors is equal to the IQ of the engineering majors. And the alternative would say the IQ of the psychology majors is not equal to 120. So again, notice the difference. The difference is that keyword difference. In the repeated measures design, as in the case of the independent measures t-test, we're focusing on the difference between conditions. In the single sample t-test, we're looking at the comparison between a known population parameter and the sample that we're going to collect data on, in this case, the average IQ of, let's say, 100 psychology majors. So I just wanted to present that to show you that sometimes students get confused because they see this 0 here. And in chapter 9, we actually had specific population parameters that we were making the comparison with. So it's important to, again, contrast these simultaneously so we can see how things have deviated for the process in this chapter in comparison to chapter 9. Figure 11.2 gives us another visual illustration of collecting the data on subjects in two different conditions. So a sample of 4 people is selected from the population. Each individual is measured twice, once in treatment 1, so this is their score in treatment 1, and then they have another score in treatment 2. Same individual, 2 different scores. And a different score is computed for each individual, this last category here. This sample of different scores is intended to represent the population. Again, inferential statistics means that we use sample statistics or sample data to draw conclusions about a population. So we don't really know what the population average difference would equal, but we're going to infer what it would equal given the sample that we have selected to test here. So note that we are using a sample of different scores to represent a population of different scores that is unknown. Also note that the mean for the population of different scores is unknown, and the null hypothesis would state that the general population different score would equal 0, meaning that there would be no consistent or systematic differences between treatment 1 and treatment 2. So again, the null would state that mu d is equal to 0. And we're going to use, again, this is the goal, is to use the sample data here, right, to infer what this value is equal to, but we're going to test the null, which indicates that there will be no difference between these conditions, that the average difference score would equal 0. Again, given our graph, mu d is equal to 0. And given the steps that we've learned thus far, the process from that point forward would be the same. We would draw our distribution, set our critical region using our alpha level, whether we're conducting a two-tailed or one-tailed test, and then the degrees of freedom to find our critical t-values, and then compute our t-statistic given our new equation of t is equal to the sample mean difference minus the population mean difference that represents the null over the estimated standard error of the mean difference, which we just learned how to calculate given our d-distribution, the sum of squared deviation scores for that distribution, and then the variance that was computed afterwards, which lends itself to the calculation of estimated standard error of the mean difference. So again, the process will then mimic what we've established back in chapter 8, and we can walk through an example from step 1, state the research null hypothesis. Step 2, set the criteria. Step 3, calculate our sample statistics, including in this case, the mean difference, and then our t-statistic, and then step 4 is to draw our conclusions based on our critical regions that have been set once we've identified the parameters. So we'll end with a quick learning check. We'll consider this scenario and then identify the correct answer. Again, one of the learning objectives of this chapter is to be able to identify when it is appropriate to use the repeated measures t-test opposed to the independent measures t-test or the single sample t-test. So let's consider this. For which of the following would a repeated measures study be appropriate? a matched subject study. So our first option is a group of twins is tested for IQ. Again, how many groups do we have? We would have two different groups because they're twins. But again, given what we understand the matched subject designed to do, this would be a viable answer that using a repeated measures t-test process would be ideal for this kind of scenario because we have two different groups, but they're twins, so they have obviously been matched up one for one based on certain characteristics. B says comparing boys and girl strength at age 3. Given that they're two independent groups, the more appropriate test to use would be the independent measures t-test. C says evaluating the difference in self-esteem between athletes and non-athletes. Again, two independent populations. The more appropriate test to apply would be the independent measures t-test. And then finally, students' knowledge is tested in September and in December. So this implies that it's the same individual and they're tested twice. So they're going to have two X values, but again, it's the same participant. So this would be also a good use of the repeated measures t-test process because again, we're working with the same individuals and each individual is going to produce two X values. And that concludes this lecture for Chapter 11. In the next video, I will walk you through an example using this process, and it'll be example 11.1 from the text, and that will illustrate a two-tailed hypothesis test using the repeated measures T process. And we'll include the calculations for the measures of effect, which include Cohen's d r squared and a confidence interval.